तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the third lecture in the module on losses in prestress. In this lecture, we shall study the long-term losses of prestress due to creep of concrete, shrinkage of concrete, and relaxation of prestressing steel. We shall also learn how to calculate the total time-dependent loss. First, the creep of concrete. The creep of concrete is defined as the increase in deformation with time under constant load. Due to the creep of concrete, the prestress in the tendon is reduced with time. The details of creep of concrete was explained in the module Introduction, Prestressing Systems and Material Properties. Here, the information is summarized. The variation of strain with time under constant axial compressive stress is represented in the following figure. Here, the time is plotted in the horizontal axis, and in the vertical axis it is the strain. When we apply the prestress, there is a immediate strain, and then there is a gradual increase in the strain with time, and if the initial stress is within a certain limit of the characteristic strength, then the increase in the strain due to creep stabilizes to a certain value. This final increase in the strain is termed as the ultimate creep strain, and which is denoted as epsilon CR ultimate. For stress in concrete less than 1/3 of the characteristic strength, the ultimate creep strain epsilon CR ultimate is found to be proportional to the elastic strain epsilon EL. The ratio of the ultimate creep strain to the elastic strain is called the ultimate creep coefficient, or simply the creep coefficient theta. Thus, here is a simple way to calculate the strain due to creep. It has been observed experimentally that the creep strain at ultimate is proportional to the elastic strain, and the proportionality constant is termed as the ultimate creep coefficient, or just simply creep coefficient. The equation is epsilon CR ultimate is equal to theta epsilon EL. The creep strain depends on several factors. It increases with the following variables: cement content, which is measured as a cement paste to the aggregate ratio. Means the more cement paste we have, there is higher chance of creep. The second is the water to cement ratio. If the water to cement ratio increases, then the strength of concrete decreases and the creep goes up. Third is the air entrainment. If there are more air pockets within the concrete, then creep increases. And the fourth is the ambient temperature. If the temperature is high, then also it is observed that creep increases. There are several factors for which the creep strain decreases. The first one is the age of concrete at the time of loading. If we delay the loading of the concrete member, whether it is the pre-stressing force or whether it is the service loads, then it is found that the creep strain is reduced. Second is the relative humidity. If the relative humidity goes up, the hydration gets better and the creep strain reduces. And the third is the volume to surface area ratio. If the volume to surface area ratio increases, which means the surface area ratio decreases, there is less loss of moisture and it is found that the creep strain decreases. The creep strain also depends on the type of aggregates. Usually for synthetic aggregates like pelletized fly ash, the creep strain can be higher. The code IS 1343-1980 gives some guidelines to estimate the ultimate creep strain in section 5.2.5. It is a simplified estimate where only one factor has been considered. The factor is the age of loading of the prestressed concrete structure. The creep coefficient theta is provided for 3 variables of the age of loading. That means the estimate that the code gives us is a simplified estimate where the ultimate creep strain is a function of only one variable, and that variable is the age of loading. What we can see that if the age of loading is 7 days, then the creep coefficient is 2.2, which means the ultimate creep strain is more than twice the elastic strain. If we load it at 28 days, then the creep strain is 1.6 times that of the elastic strain. And if we load the structure after 1 year, then the creep strain is slightly larger than the elastic strain. But at least for in all of the cases, the creep strain is higher than the elastic strain. Thus, it can be observed that if the structure is loaded at 7 days, the creep strain is more than twice the elastic strain. Even if the structure is loaded at 28 days, the creep strain is substantial. This implies higher loss of prestress and higher deflection. Now, what is the remedy to reduce the creep? Curing the concrete adequately and delaying the application of load provide long-term benefits with regards to durability, loss of prestress and deflection. In the pre-tension plants, there can be a pressure on producing the pre-tension members quickly to apply the pre-stress, that means to transfer the pre-stress quickly so as to clear the pre-stressing bed. But it is always advisable to delay the transfer of pre-stress so as to reduce creep. Let the concrete have proper hydration, and then we can expect a better performance of the concrete member with increased durability and reduced deflection. The method that is given in the code to estimate creep is simple. In special situations, detailed calculations may be necessary to monitor the creep strain with time. Specialized literature or international codes can provide guidelines for such calculations. Now, once we know the creep strain, the loss in the pre-stress due to creep is given as that delta Fp is equal to the modulus of the pre-stressing steel times the ultimate creep strain. Here we are assuming a strain compatibility of the concrete and the prestressing steel. The amount of strain the concrete undergoes, the same amount of strain the prestressing steel is reducing, and hence the drop in the prestress is equal to the modulus of the prestressing steel times the strain which we are calculating for the ultimate creep. Now, when we are doing this calculation of loss in prestress, the following considerations are applicable. First, the creep is due to the sustained loads only. The sustained loads means those are the permanent loads. Temporary loads are not considered in the calculation of creep. Usually, the dead load, which includes the self weight, is a permanent load, and a fraction of the live load may be permanent, like the furniture and the bookshelves in a library can be considered to be a sustained load. But again, in some situation, the full live load may be considered to be temporary, like in a bridge structure. Hence, appropriate judgment has to be made to consider whether the live load is sustained or what fraction of the live load is sustained, and to calculate the creep based only on the sustained load. The temporary load need not be considered to calculate the creep. The second consideration is, since the prestress vary along the length of the member, an average value of the prestress can be considered, especially for a post-tensioned member with a curved profile. The prestress can vary along the length, and because there will be a loss due to friction, but we can consider an average prestress to make the calculations simpler. And also, since the curvature of the tendon can be substantial and there can be variation of the stress in the concrete, we can consider an average value for the calculation of the creep of the full member. The third consideration is that the prestress changes due to creep, and the creep is related to the instantaneous prestress. To consider this interaction, the calculation of creep can be iterated over small time steps. We have to remember that the creep depends on the prestressing force, because the creep strain is equal to a certain factor times the elastic strain. Now, the elastic strain depends on the prestressing force. Hence, creep depends on the prestressing force. Now, what we are saying that with creep, the prestressing force is reducing. That means what we observe is that creep and prestressing force, they are interrelated. Now, we can do a refined calculation by breaking up the time span into several time steps, and we can recalculate the creep strain and the prestressing force at the end of each time step, and that will be a better calculation of the creep instead of just a lump sum calculation based on the prestress at transfer. Next, we are moving on to the second long-term loss, which is due to the shrinkage of concrete. The shrinkage of concrete is defined as the contraction due to loss of moisture. Due to the shrinkage of concrete, the prestress in the tendon is reduced with time. The shrinkage of concrete was explained in details in the module Introduction, Prestressing Systems and Material Properties. Here, we shall just summarize the shrinkage strain and how to estimate the shrinkage strain. This sketch shows the variation of shrinkage strain with time. Here T naught is the time on commencement of drying and epsilon SH is the ultimate shrinkage strain. From this curve, what is observed is that till we cure there is not much shrinkage, but once the curing stops and the member is allowed to dry, there is a shrinkage strain, and gradually this strain stabilizes to a certain value which we are representing as epsilon SH, and it is termed as the ultimate shrinkage strain. Now, like creep, shrinkage also depends on several factors. The shrinkage strain increases with the following variables. Ambient temperature. If the temperature goes up, then the loss of moisture is rapid and the shrinkage strain goes up. Second is the temperature gradient in the members. If the temperature gradient is high, then we observe that the shrinkage will be also high. Third is the water to cement ratio, and if the water to cement ratio is higher, it is a low grade of concrete, loss of moisture is high, and hence the shrinkage is also high. Cement content. Just like creep, if the cement paste to aggregate ratio is high, then the shrinkage strain goes up. The shrinkage strain decreases with the following variables. Age of concrete at commencement of drying. That means if we cure the concrete for a longer period, and then if we apply the pre-stress or put it into service, then shrinkage is low. Next is relative humidity. If the relative humidity goes up, then hydration is better, loss of moisture is less, and shrinkage will be also less. Third, volume to surface area ratio. If the surface area ratio decreases, this volume to surface area ratio increases, and what we observe that the loss of moisture is less, and hence the shrinkage is also less. The shrinkage also depends on the type of aggregates used for making the concrete. IS 1343-1980 gives guidelines to estimate the shrinkage strain in section 5.2.4. It is a simplified estimate of the ultimate shrinkage strain. For pre-tension members, epsilon SH is equal to 0.0003, and for post-tension members, epsilon SH is equal to 0.0002 divided by the logarithm of T plus 2, where T is the age of concrete at transfer in days, which approximates the curing time. Here also what we observe that if we increase the curing time and delay the transfer of pre-stress, then T will increase and hence epsilon SH will decrease. Thus, with increasing age at transfer, the shrinkage strain reduces. Curing the concrete adequately and delaying the application of load provide long-term benefits with regards to durability and loss of pre-stress. Just as we have seen for creep, similarly for shrinkage, if the concrete member is properly cured and then if the pre-stress is transferred, then the shrinkage strain will be less, the durability of the member will be better, and the deflections will get reduced. In special situations, detailed calculations may be necessary to monitor shrinkage strain with time. Specialized literature or international codes can provide guidelines for such calculations. The shrinkage is of a concern for liquid retaining structures, where shrinkage cracking can be a problem because the liquid can come out or can percolate out through those cracks, and that will lead to a problem of durability of the liquid retaining structure. The loss in pre-stress, which is termed as delta Fp, due to shrinkage is given as the modulus of the pre-stressing steel times the shrinkage strain. Here also we are assuming compatibility between the strain in the concrete and the steel. That means if epsilon Sh is the strain in concrete due to shrinkage, then the pre-stressing steel also has a strain which is equal to epsilon Sh. I would say a change in strain which is equal to epsilon Sh, and the loss in the pre-stress is equal to the change in the strain times the modulus, and that will give the loss in the pre-stressing force in the tendons. The third type of long-term loss is the relaxation of steel. Relaxation of steel is defined as the decrease in stress with time under constant strain. Due to the relaxation of steel, the pre-stress in the tendon is reduced with time. Just like creep, relaxation also depends on time. It depends on the type of steel, initial amount of pre-stress, which is denoted as FPI, and the temperature. This figure shows the variation of the stress with time for different levels of pre-stressing. In the horizontal axis, we are plotting the time in a logarithmic scale, and in the vertical axis, we are plotting the pre-stress which is changing with time normalized with the initial pre-stress. What we observe is that if the initial pre-stress is about 60% of the characteristic strength, then the change in the pre-stress is almost imperceptible. That means the relaxation loss is insignificant. But if the initial pre-stress is increased, if it is 70% of the characteristic strength, then we can notice a drop in the pre-stress. And for 80% of the characteristic strength, the drop is substantial, and when we go for a initial pre-stress which is equal to 90% of the characteristic strength, the drop is extremely high, and that is not safe for the structure. Thus, it can be observed that there is significant relaxation loss when the applied stress is more than 70% of the characteristic tensile strength of the pre-stressing steel. Hence, the code limits us to have a maximum value of the pre-stress which is based on safety and also from the consideration of relaxation loss in the tendons. The calculation of the drop or loss in pre-stress was explained in the module of interaction, pre-stressing systems and material properties. In the absence of test data, the recommendations of IS 1343-1980 can be followed. The relaxation loss is given for 1000 hours and for a temperature of 27 degrees Celsius. If the initial pre-stress is 50% of the characteristic strength, then the relaxation loss is negligible. It can be considered to be 0. If the initial stress is 60% of the characteristic strength, relaxation loss is 35 Newton per millimeter square. If the initial stress is 70% of the characteristic strength, then the relaxation loss is 70 Newton per millimeter square, and if the initial stress goes to the maximum limit, which is the 80% of the characteristic strength, then the relaxation loss is 90 Newton per millimeter square. Again, what we can see that this relaxation loss is a lump sum estimate which is not depending on the type of steel. If we need more detailed calculation of the relaxation loss based on the type of steel, we can either get the information from the supplier of the steel, or else we can do some tests in the laboratory to find out the relaxation loss, and we can also monitor the drop in the pre-stress with time. Now let's understand the calculation of this long-term loss by a simple example. A concrete beam of dimension 100 mm by 300 mm is post-tensioned with 5 wires of 7 mm diameter. The average pre-stress after short-term losses is 70% of the characteristic strength, which is equal to 1200 Newton per millimeter square, and the age of loading is given as 28 days after the casting of the concrete. Given that the modulus of the pre-stressing steel is equal to 200 times 10 to the power 3 megapascal, and the modulus of concrete is equal to 35,000 megapascal, find out the losses of pre-stress due to creep, shrinkage and relaxation. Note that here we are not calculating the short-term losses, we are just calculating the long-term losses. Now, before we start the calculations, we need to find out the geometric properties. Here the location of the CGS is given. It is 50 millimeters below the centroid of the section. That means the eccentricity of the centroid of the CGS is 50 millimeters. We are calculating the area of concrete, which is 100 times 300, that is 30,000 millimeter square. Next, we are calculating the moment of inertia of the beam, which is 100 times 300 cube divided by 12 equal to 225 into 10 to the power 6 millimeter to the power 4. The total area of pre-stressing steel is equal to 5 times the area of each wear. The area of each wear is given as pi by 4 times the diameter square, and thus the total area of the pre-stressing steel is 192.42 millimeter square. The pre-stressing force after the short-term losses is equal to the area of the pre-stressing steel times the pre-stress, which is equal to 192.4 times 1200, and which gives me 230.88 kilonewtons. That means this is the initial pre-stress after the short-term losses. And now we are calculating the drop in the pre-stress due to each of the long-term loss, and then we shall try to find out an estimate of the total drop in the pre-stressing force. We are calculating the modular ratio, which is the ratio of the modulus of the pre-stressing steel and the concrete, and that is equal to 5.71. Next, our objective is to find out the stress in concrete at the level of CGS. So remember that when we are calculating the creep strain, we first need to know the elastic strain, because then we multiply the elastic strain by the creep coefficient to get the ultimate creep strain. Now, in order to get the elastic strain, we need to know the stress in the concrete at the level of the CGS, and the stress is given as minus P0 by A, which is a term constant throughout the depth of the section, and the second one is P0E times E by I. This is a term which generates due to the eccentricity of the tendon. E is the eccentricity of the tendon, P0 times E is the moment due to the eccentricity, and since we are finding out the stress at the level of the CGS, the distance that we are interested in is also equal to the eccentricity. Now, once we substitute the force, the eccentricity and the geometric properties, we find that the stress in the concrete at the level of the CGS is equal to minus 10 to the power 10.25 Newton per millimeter square. It is the compressive stress which is of magnitude 10.25 Newton per millimeter square. Thus, we have found out the stress in the concrete, from where we shall calculate the elastic strain, which will help us to calculate the creep strain. The loss of pre-stress due to creep is equal to delta Fp with subscript Cr equal to Ep times the ultimate creep strain. We are substituting the ultimate creep strain by the creep coefficient times the elastic strain. Then we are substituting the elastic strain by the pre-stress divided, not the stress in the concrete divided by the modulus. This is the Hooke's law we are substituting, and the ratio of EP by EC we can substitute by the modular ratio. Thus, the creep, the loss of pre-stress due to creep is equal to M times Fc times theta, and when we substitute the values, we get a drop in the pre-stress which is equal to 93.64 Newton per millimeter square. This is the long-term loss of pre-stress after a substantial time, say after 5 years, and this is the can be considered to be the loss due to creep strain alone. Now, we have picked up a value of theta is equal to 1.6 for loading at 28 days from table 2C1, which is also given in clause 5.2.5.1 of IS 1343/1980. That means we need to know the age of loading before we can calculate the creep strain, because that is a very important factor for the variation of the creep strain. Second, we are calculating the shrinkage strain from clause 5.2.4.1 of the code IS 1343/1980. Since it is a post-tension member, the creep strain is given as 0.0002 divided by the logarithm of t plus 2, and t is 28 days. Once we substitute that, we are able to find out the shrinkage strain in the member. Now, this shrinkage strain is uniform throughout the depth of the section. Hence, it is the same value at the level of the CGS. The loss of pre-stress due to shrinkage is given as delta Fp with subscript Sh equal to the shrinkage strain times the modulus of the pre-stressing steel. And once we substitute the two values, we get a loss of pre-stress which is equal to 27.08 Newton per millimeter square. Third, we are calculating the loss of pre-stress due to relaxation from table 2C2, which is same as table 4 of IS 1343. We find for an initial stress of 70% of the characteristic strength, delta Fp subscript RL is equal to 70 Newton per millimeter square. We have calculated the loss of the pre-stress for the creep, shrinkage and relaxation individually. Next, we are calculating the loss of the pre-stressing force. The loss of the pre-stressing force is given as the drop in the pre-stress times the area of the pre-stressing steel. The loss of pre-stressing force due to creep is equal to 93.64, which is the drop in pre-stress due to creep times the area of the pre-stressing steel, which is equal to 18,018 Newton. Next, the loss of pre-stressing force due to shrinkage is equal to 27.08 times 192.42, which is 5,211 Newton. The loss of pre-stressing force due to relaxation is equal to 70 times 192.42, which is 13,469 Newtons. Thus, we have calculated the loss of the pre-stressing force due to the creep, shrinkage and relaxation individually. If we try to find out the total long-term loss of the pre-stressing force, a simple way is to overestimate the total loss by neglecting the interaction of the losses and the pre-stressing force. We are adding the individual losses together and we get a total long-term loss of 36,698 Newtons. The percentage loss of pre-stress is equal to this total drop divided by the pre-stress at transfer after short-term losses times 100%, and which comes around 16%. Thus, what we can observe that first, that when we are applying the pre-stress, there is a short-term loss due to the friction, anchorage slip and elastic shortening. We have seen that for a pre-tension member, the elastic shortening loss can be substantial. For a post-tension member, the friction and the anchorage slip can be substantial, especially if the post-tension member is long. And now we are observing that the long-term loss, which happens over a substantial period, can also be substantial. Here we can see that the drop in pre-stress is 16%. Now, this was the reason why the prestressed concrete initially was not getting the confidence, because it was observed that the effective prestress was reducing with time, and in the earlier days before the use of high strength steel, the effective prestress almost became zero. To circumvent this problem, the solution was to use high strength steel and along with high strength concrete, for which, although after the loss of the prestress with time, there will be a residual prestress which will be satisfactory for the service loads. Next, we are calculating the total time dependent loss. What I had mentioned before, that the loss of prestress and the individual phenomena of creep or relaxation, they are dependent on each other. That means the creep strain is dependent on the elastic strain, which is dependent on the prestressing force. On the other hand, prestressing force reduces due to the creep strain. Similarly, the relaxation, that once there is a relaxation, the prestressing force will drop, that will affect the creep, and hence what we observe that creep, shrinkage, relaxation and the prestressing force, they are interrelated. The way we had calculated earlier, where we calculated each loss separately and we just added them up, this will give an overestimate of the prestressing loss. The result may be adequate for simple construction, but when we are doing the calculations for more important structures, then we have to refine our calculations to include the interaction of the creep, shrinkage, relaxation on the prestressing force. Now, to consider this interrelationship of the cause and effect, the calculation can be done for discrete time steps. what we had seen before, that the phenomenon of creep, shrinkage, relaxation are all dependent on time. But the estimates that are given in the code IS 1343, they are simple estimates where the values are given only for the ultimate, and the time does not appear as a function for any one of the losses. But if we want to do the calculations more accurately, we have to use discrete time steps, where we also need to have expressions of creep, shrinkage and relaxation as a function of time, and such expressions are available in the specialized literature or the international codes, with which we can monitor each individual loss with time. The results at the end of each time step are used for the next time step. That means the basic idea is that we have discretized the service life into several time steps, and we are calculating the loss at the end of each time step by assuming that the prestressing force is constant over that time step. Now, once we have computed the loss at the end of one time step, we are recalculating the prestressing force, and that new value of the prestressing force becomes effective for the next time step. That means when we are doing the calculations for the next time step, we use this new value of the prestressing force, we calculate the losses at the end of that second time step, and from that losses we again recompute the prestressing force. That means the calculation goes step by step, by which we are able to incorporate the interrelationship between the creep, shrinkage, relaxation and the drop in the prestressing force. This step-by-step procedure was suggested by the Precast Prestressed Concrete Institute Committee and is called the general method. We know that this Precast Prestressed Concrete Institute, in short PCI, is a professional organization to promote prestressed and precast concrete, which is based in United States, and the following method is called the general method, and it has been given in a paper written by the PCI committee, and the title of the paper is Recommendations for Estimating Prestressed Losses. It was published in the PCI Journal, volume 20, number 4, in the months of July, August 1975, and the pages are from 43 to 75. Now, in the PCI step-by-step method, a minimum of 4 time steps are considered in the service life of a prestressed member. So, as I said before, that the procedure is that we are discretizing the service life of a structure into several time steps. Now, what the method suggests, that the minimum number of time steps that we need to consider is 4, and this discretization is a rational discretization based on the variation of creep, shrinkage with time. That is why in the initial period the discretized steps are small, and then the steps are larger because the variation of creep and shrinkage gets stabilized with time. The time steps are: the first time step starts with the anchorage of the steel for a pre-tensioned member, and for a post-tension member it starts with the end of curing. The end of the first time step is the age of prestressing. That means for a pre-tension member, once we have anchored the steel, we take some time to cast the concrete, cure the concrete, cut the steel and transfer the prestress. but by that time there is some relaxation loss of the steel because it has been held against the end abutments. Now, for the post tensioned, once we have cured the concrete and we are applying the pre-stress after a certain time, then we may have some change in the strain, and we may note that if the difference between the end of curing and the age of pre-stressing is substantial. If the pre-stressing is done right after the end of curing, then we may not consider any long-term loss in that first time step. The second time step starts at the end of first step, that means it starts at the age of pre-stressing and it ends at 30 days after pre-stressing or when subjected to superimposed load. That means in the first month the creep and shrinkage can be substantial, and hence we are evaluating the losses over the first 30 days, or if the time to the imposing the load is larger than 30 days, then we may consider the period from the age of pre-stressing to the time when the member is subjected to the superimposed load. This period is say roughly around 30 days or slightly more, and it is a small time step because there is a large variation of the pre-stressing force due to creep and shrinkage in the first month after the pre-stressing of the concrete member. The third time step starts from the end of the second time step, that means after 30 days after pre-stressing, to the first year of service. That means again our third time step considers the loss of pre-stress for the first service year, because it has been found that creep and shrinkage can be substantial in the first year of the service, and hence we need to recompute the pre-stressing force after the first year of service. And finally, the fourth time step starts with the end of the third time step, which is the first year of service, and it ends with the end of service life, which may be say 50 years. To summarize, that creep, shrinkage, relaxation, they are related to the drop in the pre-stressing force. If we calculate the losses individually and add them up, that is an overestimate of the total pre-stressing loss. For important structures, we need to do a more precise calculation considering the interaction between the creep, shrinkage, relaxation and the drop in the pre-stressing force. The method to do this is the step-by-step method, which has been proposed by the PCI committee. In the step-by-step method, we need to discretize the service life of the pre-stressed member into minimum of 4 steps, and this division is based on the variation of the creep and shrinkage. The first time step is crucial for the pre-tensioned members, wherein there can be relaxation after the stretching of the tendons and until the pre-stressing is transferred to the concrete member, there can be a drop in the pre-stress due to relaxation. The first time step may not be crucial for a post-tension member if the age of pre-stressing is right after the end of curing. The second time step is from the age of pre-stressing to 30 days after pre-stressing. Since the creep, shrinkage vary quite substantial in this first month, that's why the first time step is after the first month where we calculate the creep, shrinkage and relaxation losses and recompute the pre-stressing force. The third time step starts from the end of the first month and ends at the first year of the service life. Here also what we observe that in the first year of service life the losses can be substantial, and hence we need to recompute the pre-stressing force after the first year of the service life. And finally, in the fourth time step, we are starting at the end of the first year and we are doing the calculations of the total loss after the substantial period, which is say equal to the end of the service life of the structure, which will give the final values of the creep, shrinkage and the relaxation loss and the drop of the pre-stressing force. Now, the step-by-step procedure can be implemented by a computer program where the number of time steps can be increased. Now, several such programs are being written and they are available commercially, and this can be used by the users of a precast or a prestressed industry, and it has to be checked whether which code they are following and which procedure they are following, and after that these programs can be used to have a more detailed calculation of the losses due to creep, shrinkage and relaxation, and to monitor the pre-stressing force with time. As we know that when we are calculating the stresses in the concrete at the stages of transfer, at the intermediate stages and at service, the pre-stressing force can be different. If we are able to monitor the pre-stressing force with time, then we can have more accurate prediction of the stresses in the pre-stressed member, which includes the effect of the losses due to creep, shrinkage and relaxation. There are also approximate methods to calculate lump sum estimates of the total loss, which considers the interaction of the creep, shrinkage, relaxation with the drop in the pre-stressing force. But since these estimates are not given in IS 1343, they are not mentioned here. In case if somebody is interested in using these methods, then they can use the methods recommended by the PCI committee or which are published in some recognized publication. Today, we studied the loss of pre-stress due to the long-term effects. First, we studied the loss of pre-stress due to the creep of concrete. The creep is defined as the increase in strain in the concrete under a constant stress, and what we have seen that if the stress is limited within a certain value of the characteristic strength, then the ultimate creep strain is almost proportional to the elastic strain, and the estimation of the ultimate creep strain is given by a simple expression. The ultimate creep strain is equal to a proportionality constant times the elastic strain. The proportionality constant is called the creep coefficient. Now, the creep depends on several factors. It increases with a few variables and decreases with a few other variables. The code IS 1343 gives a simple procedure to estimate the ultimate creep strain. There, the coefficient is a function of only one variable, which is the age at which the pre-stress is transferred. And what we have observed that if the age is large, then the creep is reduced. Hence, if we have to reduce the loss of pre-stress due to creep, then we can cure the concrete for a longer period and delay the transfer of pre-stress. This will have long-term benefits of durability also. The loss of pre-stress is calculated from the creep strain by multiplying it with the modulus of the prestressing steel. Here we assume a strain compatibility between the concrete at the level of the CGS with that of the steel, and once we know the drop in the prestress, we can calculate the loss of the prestressing force by multiplying the drop in the prestress with the area of the prestressing steel. The second loss that we have studied was the shrinkage of concrete. The shrinkage of concrete is the reduction of volume or the reduction of length with time due to the loss of moisture. Like creep, shrinkage also depends on several variables, and it increases with some of the variables and it decreases with some of the variables. The code IS 1343 gives a simple estimate of the creep strain. For a pretension member, it is higher, which is 0.0003. For a post-tension member, it is lower, but it depends on the age of concrete at transfer. It has been assumed that that age is the end of the curing period. Now, once we estimate the shrinkage strain, we can find out the loss in the prestress due to by the multiplying that shrinkage strain by the modulus of the steel, and that will give the loss of the prestressing force, which is equal to the loss of prestress times the area of the prestressing steel. The third type of long-term loss we studied was due to the relaxation of steel, which is the drop in stress at constant strain, and the relaxation also depends on the type of steel, the amount of initial prestress, and the temperature. We have found that if the initial prestress is very high, if it is equal to 70% or more than the characteristic strength, then the relaxation losses can be substantial. Hence, the code limits us the prestress to about 80% of the characteristic strength for the safety reasons, as well as to limit the loss of prestress. Now, the code gives us simple estimates of the relaxation loss, which is a function of the initial prestressing force, and what we can see that if the initial prestressing force is 70% or more, then the relaxation losses can be substantial. The loss in the prestressing force is equal to the drop in the prestress times the area of the prestressing steel. We can have an estimate of the total long-term loss by adding them up, but if we want to have a refined calculation, then we have to adopt a more accurate procedure. We have learned the step-by-step procedure suggested by the PCI, where the time is discretized into small steps and we iterate, and which incorporates the interaction of the creep, shrinkage, and relaxation with the prestressing force. With this, we are ending the losses of prestress, and in the next lecture we are entering the third module, which is the analysis of prestressed concrete members. Thank you.